Okay, so let's get started with week 10 of Fundamentals of Convective Heat Transfer. This course is being instructed by Professor Amaresh Dalal from the Department of Mechanical Engineering at IIT Guwahati. My name is Debjit. I'm a PhD scholar at IIT Madras, and like every other week, we shall be solving some problems together. So let's get into it. We will first look at problem number 1. Okay, so first of all, this week the discussion has been on numerical solutions of heat transfer problems, specifically convective heat transfer problems. Now, up until this week, we have been looking at analytical solutions, but there are many cases where we cannot rely on or we cannot go forward with analytical solutions, which is why we have to rely on numerical solutions. They can handle a lot of complex geometries and complex flow situations, different physical problems coupled together. So these are really important in industrial scenarios as well as in academic uh, research problems. So that is why this is really important. Now we looked at some very basics and fundamentals of numerical solutions. So this question also pertains to one of the very simplest of things. So most of these physical problems that we're dealing with, they are governed by these partial differential equations, right? These partial differential equations. Now PDEs can be classified into parabolic, hyperbolic, or elliptic, and they correspond to problems which can be described as equilibrium problems or marching problems. Now here we have two columns, including the type of physical problems and the types of partial differential equations. So you have to match the two columns, and one item can correspond to more than one item. So the combinations are available in the options below. So they are option A, A1, B2, option B, A2, B3, option C, A3, and B1 as well as 2, or option D, A corresponding to both 1 and 2, and B corresponding to 3, where A is march equilibrium problems, B is marching problems, and 1, 2, and 3 refer to parabolic, hyperbolic, and elliptic PDEs, respectively. So which one? So match the options correctly and then try to find the correct combination among the four options given A, B, C, D. Then once you have picked the correct combination, you can lock in your answer. So let's take a look at the correct solution. It's actually option C. So let's go through these one by one. So parabolic PDs, these are generally marching problems. Hyperbolic PDs are marching problems as well because they both of them evolve in time, sort of. If time is the marching direction, there could be exceptions where you can march in the spatial direction as well. So the boundary layer equations are is an example of that sort. And elliptic PDs generally correspond to equilibrium problems, something like temperature conduction or diffusion of some concentration. Those are equilibrium problems. So 1 and 2 correspond to B and A corresponds to 3. So that is option C, A3 and B1, 2. Right. Okay. So moving on, we'll move on to question number 2 now, which is asking us which of these are numerical schemes used for solving convective heat transfer problems. Is it option A, finite difference method? Is it option B, finite element method? Is it option C, finite volume method? Or is it option D, all of the above? It's a simple one. Let's take a look at the solution. It's actually all of the above. In the lectures, we already saw glimpses of the finite difference as well as finite volume method. And although we did not discuss, but finite element method is also used in order to solve fluid flow as well as heat transfer problems. So the correct answer should be option D, all of the above. All right. So moving on to question number 3 now. Question number 3 is asking us what is the order of accuracy of forward difference discretization scheme? Is it option A 1? Is it option B 2? Or is it option C insufficient information? So let's say I'm using forward this difference discretization, and this is my, let's say, delta x. And what is the order of accuracy? Is it order 1? Is it order 2? Or is it something else? Or is there not sufficient information being given in this question in the first place? So the correct answer would be insufficient information, because it really does not depend on forward difference alone. It also depends on how many points you are considering. So let's say you can use 2 points. So for point I, if you are calculating, you can take 2 points, I plus 1 and I plus 2, and then get a second order accurate scheme. Similarly, if you had used only 2 points, let's say I and I plus 1, then you would get only order 1 accuracy. Similarly, you could use n number of points and hopefully get n order of accuracy as well. So since that wasn't mentioned, therefore this question does not give you the sufficient information. So your correct option should have been option C, that is insufficient information. Okay, so moving on to question number 4, we are asking whether explicit schemes are, uh, it's a question on the stability of explicit schemes. Are they option A unconditionally stable, option B unconditionally unstable, or option C conditionally stable? So taking a look at the solution, they are conditionally stable. So we saw that, in one of the examples, that, so first of all, the CFL criteria, the Courant, Friedrich, and Levy criteria is often required in order for the explicit schemes of fluid flow to be conditionally to be stable. So since it depends on this condition, uh, they are conditionally stable. On the other hand, in implicit schemes, mostly they are unconditionally stable. Like, it does not matter what size of grade or what time step you take, the solution would at least be stable. They won't be very fine grained or accurate, but at least they will be stable. So that is one of the benefits of implicit schemes, and in many cases in practice we use implicit schemes instead of explicit schemes, right? Okay, so moving on, we'll move on to how are implicit schemes solved. Are they solved by option A, Kramer's rule, option B, Gauss elimination, option C, Jacobi method, option D, Gauss-Seidel method, or is it option E, all of these? Taking a look at the solution, these are all methods by which implicit schemes can be solved. Now, there is a certain category within them. So Kramer's rule and Gauss elimination, these are direct methods. They are more time taking, which is why seldom used. And Jacobi method and Gauss-Seidel method, these are iterative methods, and these can be found more commonly in practice. But direct methods are more accurate, whereas iterative methods you have to set some, tolerance level for errors. So let's say that tolerance, if I call it tau, it has to be less than equal to, let's say, some 10 power minus 6. This is the tolerance of error that I set. and I'll keep iterating until and unless I meet this condition. Okay. All right. So moving on, move on to now the MAC algorithm. Now the thing is, in MAC algorithm, you have to follow these steps in a certain order. We have given the steps A, B, C, D, E, and F. You have to arrange them in the correct order, which is used in MAC algorithm, also known as marker and cell method or marker and cell algorithm. Different combinations are given here in the right hand column. So let's take a look at the steps. The steps are step A, initialize U, V, W, P, and T. Option B, check for convergence and repeat if necessary. Option C or step C is to predict provisional velocities. Step D is solve for scalars. Uh, for example, pressure and temperature, not pressure, temperature and other scalars. Step E, that is update the velocities, and step F, that is find the pressure correction. So arrange them in an order which is correct for marker and cell method. There can be, of course, many combinations of these 6 steps. We have given only 6 combinations in the options, so you can pick from there whichever you feel is correct. The options are, option A is A, B, C, D, E, F, that is exactly in the order given. It could be option B, A, C, F, E, D, B. It could be option C, A, F, C, D, E, B, or option D, A, C, E, F, D, B. So let's take a look at the solution. It's actually option B. We'll reach there. So let's first look at the algorithm. So initializing is anyway the first step. So this is step 1. Then in the next step, you have to predict the provisional velocities while ignoring pressure. So that is step 2. Then you have to find the pressure correction terms in terms of the provisional velocities. So that is step 3. Then once you have the pressure correction, you have to update the pressure first and then use them to update the velocities. So this becomes the 4th step. Then once you have the velocities, then you can solve for the scalars. That is step 5. And ultimately you have to check for convergence and repeat. You have to keep on repeating these cycle of steps until you reach the tolerance level for error. So check for convergence is where you calculate the error and uh, check whether the error is lower than your tolerance or not. So using this, so I have step 1 is A, 2 is predict, sorry. Uh, so we have A is 1, then 2 is C, 3 is F, 4 is E, then 5 is D, and last step 6 is B. So ACF EDB, ACF EDB, that is the correct solution. So this is all about the MAC algorithm. Now moving on to question number 7, which is asking us about the problems of using a co-located grid. Is it option A checkerboard pattern, option B, pressure velocity decoupling, is it option C, both A and B, or is it option D, none of the above? So let's take a look at the solution. It's actually option C, both A and B. So in co-located grid, what we do is if we have a grid like this, we store the pressures as well as the velocities in the center of the cell. So if, for example, if there's a checkerboard pattern, let's say the pressure, if I put 200 here, 100 here, and 200 here, while computing the U here, I will see, let's say I'll call this P1 and P2. Then here if I need to calculate the dou p dou x at, so I'll call them I minus 1 and I plus 1. So dou p dou x at I'll have something like p2 minus p1 by 2 delta x. Then I'll get 200 minus 200 by whatever. This will be 0. So it would seem as if there is no pressure gradient here, but as you can see from the numbers that there is a wave-like pressure gradient here. It's 100 here and 200 in both of its neighbors. But using a collocated grid makes it blind to such pressure gradients. So checkerboard patterns in both velocity or pressure if it arises, then a collocated grid is not able to handle it. And a related problem is this pressure velocity decoupling, where the pressure and velocity, they do not talk to each other. So that is another reason why staggered grids are used, because they couple these pressure and velocities in a more natural way. So both A and B are problems with using collocated grid. As a result, option C, both A and B, would be the correct answer. Okay. So moving on, we move on to question number 8, which is asking us what are the different upwind schemes which are commonly used in numerical solution for convective heat transfer. Is it option A, first order upwind schemes? Is it option B, second order upwind schemes? Is it option C, quick scheme? Or is it option D, all of these? And the simple answer to that is all of these. So these are all different ways of solving problems in an upwind manner. Okay, so that was the last question of today's session. Thank you very much. We'll meet again next week.